All right, everyone. We are going to wait a few minutes because we are supposedly being joined by a few visitors today. All right, it looks like Kyle is here, and someone from Alumni Affairs is here. And it is 9 o'clock, so let's get started. Today we're going to do something a little bit different. We're going to give the first 10, 15 minutes or however long people have questions for to a recent graduate of this department, Kyle Haddock, class of 2018. Kyle took this class and then he did a senior project on things related to this class. And now he is working at Opto on thin film coatings. And since the topic of today's class is thin film coatings, I thought it would be appropriate to have him talk a little bit about what he does. So Kyle, I'm gonna let you take over. And if you want, I should be able to make it so that you can do a screen share there.
Yeah, can you hear me right now?
Yeah, I can hear you.
Okay, great. Yeah, let me go ahead and share my screen so I can bring up my presentation. Okay, I'll bring up that. Sorry. Okay. Hi, everyone. My name's Kyle. I'm a recent graduate. I graduated in 2018 from the physics department at Cal Poly Pomona. Dr. Small was my teacher at least 4 times, I think. I took him for applied optics as well as the computational physics and mechanics as well. I currently work at the Opto Corporation as an application engineer. I always thought it was funny that I got a degree in physics and I still have engineer in my job title, but many of you will probably have the same outcome as well. So I just want to prepare you all for that. So I just want to tell you a little bit about what Opto is and what we do there. It's established in 1995. It's located in Santa Ana, Orange County. Most of our manufacturing is done in Japan and a little bit done in China. We have our own optical coating lab in Santa Ana, as Dr. Small was alluding to. And we serve many industries ranging from medical, aesthetic lasers, industrial machining, laser machining, aerospace, astronomy, optical metrology, many different fields we serve. And the type of products we make are mostly optics, Opto-Mechanics, which are basically allow you to control your optics with precision control, manual and motorized positioners, as well as optical coatings. So I'm just going to show you a few slides about, they're taken directly from our website. So as you can see, we do electric mirrors, we do metal mirrors, we do lenses, aspherical, spherical, do achromatic doublets. We do focusing lenses that are multi-element, can be 3, 4 elements sometimes. We do cube beam splitters and as well as plate beam splitters as well, filters, filter glass. We do polarizers, anything with polarization control, objective lenses, so anything you would put onto a microscope. I didn't put it on here, but we also make microscopes as well. And then we have optical assemblies, which is basically multi-element optics, and then prisms and stuff like that. So the Opto-Mechanics is essentially anything that you would use to control your optics or mirrors with precision control. This is what you would allow you to do that. And so these are kind of just give you some examples of what allows you to control your optics. And then again, manual positioners is kind of what it alludes to. It allows you to move something with precise control over a certain axis or rotation range. The goniometers are really interesting because they allow you to move about a center point. So essentially you would kind of like rotate under this center point like that. Last, we have motorized positioners, which is essentially the same thing as the manual positioners, but the motorized allows you to have computer control. Some of these can have resolution down to 100 nanometers. So you can do a precise step of 100 nanometers. So I think that's a pretty interesting find. I didn't know about this before I started working here. So essentially what I do is I have to be knowledgeable about all of those things I just showed you. We have over 15,000 items in the catalog, and a lot of times, or a lot of the time when I first spent there was just researching all about these items that I had no idea about. So I took all my optics and physics background knowledge, and then I just really just plugged it into just absorbing what all these different items do and how people use them and why they're useful. So that's basically one of the main things I do is I provide technical support. So customer will call in and say, hey, I'm doing this kind of experiment. What do you recommend for, this kind of lens, or I'm having this kind of issue? And then I basically kind of talk with them and discuss what issues they're having and how basically I can provide a solution or a product, or point them into the direction of a product that will make give them a solution for the problem they're having. And as Dr. Small was alluding to, I do some designing for optical coatings, and that's really cool too. So when I took this applied optics class, I was introduced to the Python code. I'm not sure if you guys started using the Python code yet?
Yeah.
So I was introduced to the Python code, and I just had a lot of fun just playing around with just plugging in different layer thicknesses, different materials, and seeing what the outcome would be. And then from there, I moved on to doing a senior project with Dr. Small, where basically I was using the Python code to simulate optical filters that were already been published in patents and stuff like that. And then I was essentially trying to figure out how much error there could be between the design and how the actual run comes out. And then that is basically when I went to go interview for this job and they heard about that, they were like, wow, because that's something that we do all the time at Opto Sigma is the design. Sometimes it comes out exactly as you design it, and sometimes there's just something weird about the run, and you just have to play around with it and troubleshoot until you get it to work just right. So when I learned to do optical coatings, I got to take a class in Tucson taught by this man named Angus McLeod. I'm just going to go into the next page. So yeah, so I was first introduced to optical coatings in the same class you guys are taking. And then my senior research project was focused on simulating the optical coatings using Python. So, and then I want to say within 4 or 5 months of me being at Opto Sigma, they thought I had enough, I guess, smarts to go and take this class taught by Angus McLeod. And so basically it was a 5-day class where 8 hours a day where we learned to use this software to basically, it's basically a full.
The sound is cutting out. The sound is cutting out. Can anybody hear Kyle? I can't.
I can't either.
What?
We can't hear him either.
Okay. What's going on here?
Can you guys hear me?
Now we can.
Okay. Where did I leave off?
You just started saying that you were going to his class and learning Angus MacLeod's software.
Oh, okay, yeah. So basically, the software it's just basically a full software version of what you guys do with the Python code. So it already has all the basic materials in there. But if you want to add in some specific like shot glass types or something like that, you have to kind of download it, get the refractive index information from the internet, or sometimes you can download it through the software. But basically, the whole week we spent learning how to design different kinds of filters, how to optimize the filters. It was really neat, and I learned a lot from that class. And then, I think last fall I got to go to Japan to learn from our optical coating team there, as well as to learn about our manufacturing. And so that was absolutely an incredible experience. I'm gonna go on to the next slide right here. So our facility, we have the 3 chambers. If you see on the very right, there's like a door that's covered in aluminum foil. That's going to be a chamber right there. And then the one to the left of it, where there's the computer with the time, and then the one all the way directly across. And so these ones are about, I would say, 5 feet by 4 feet. But some of the ones in Japan can be anywhere from 10 to 8 feet, or about like, I think they said it was about 2 by 4 meters or something like that. So the chambers can get absolutely enormous in size, and they can code up to like 500 parts in one, versus ours can code about 100 to 200 at a single time. And then type of
Could you say
coatings
a little more about a coating chamber? We haven't really talked about what that is yet in this class.
Yeah, sure. So there's many different types of coating chambers. So the types that we have at Opto Sigma, we have 2 that use what's called E-beam evaporation. So would be called a physical vapor deposition, PVD process. And so that's one of the main kinds you see, and that's basically because we focus on the dielectric coatings, as it kind of says in the slide right here. And so physical vapor deposition is kind of the go-to for the dielectric coatings. And then basically the way that the E-beam evaporation works is that it takes an E-beam source, electron beam source, and it focuses this with a very powerful electromagnet into like a little cup that has the coating material. And so the electron beam in here just comes and absolutely brings it up to a melting temperature or evaporation temperature within seconds. And so immediately you have the coating just shooting off from this little pocket up onto the substrates that are immediately above. I should have put a slide in here about what the chambers look like. I apologize.
It's okay.
And so yes, but then that's one style. So that's the E-beam. But then there's other kinds called like an IBS, which is ion beam sputtering. So instead of an electron beam, it uses a heavily focused ion beam, and it uses these sputter targets, which are like probably about 6 to 8 inches in diameter, and it bombards this big target with the heavily focused ion beam, and then again the particles just kind of spray off of the surface and then go onto the substrates that you're trying to coat. And then we use a lot of the higher end stuff. We'll use some kind of technology to compact the film, because essentially, if you can imagine SiO2 has a refractive index, a bulk index of like about 1.45, very similar to fused silica. But when you actually go to do this in the chamber, you don't get exactly that, because you don't get the same packing density as what you would with a real film. And so basically you end up with a slight difference in refractive index, but you can get it almost to be the nearly like about 95% of the refractive index that it should be, by using a technology called IAD, which is ion assisted deposition, and it basically sends ionized particles to compact the film while you're coating at the same time. So that can be done many of the newer processes use a plasma to do this, and then we use like an ion beam source. or like an ion, yeah, just like a source, I guess.
All
So, yeah.
right. Oh, did you have more?
I was just going to say we do many coatings at Opto Sigma, ranging from anti-reflective, highly reflective, partial reflector, beam splitter, dichroic, and we also do stuff for high-powered lasers as well. So that's one of the things that gets me really excited about doing my job is knowing that I'm going to design something or design a coating that's going to get used by, a really crazy laser.
Okay, well, we've got time for questions. Anyone wants to ask, just unmute your mic and ask away. I've got one to start off. What's it like working there right now during quarantine? How much of your work are you able to do remotely?
So right now, working from home has been okay. I'm sure many people have the same experience. I really actually like going into the office. I mean, I have a nice apartment, but it's getting a little too much of the same. So, um, but yeah, it's cool. I mean, I can do most of what I do there. The only kind of thing that's slowing me down is this computer that I'm using. The computer I use at work, like by default, has to be really powerful because I use programs like Zmax or the coding design software that uses the optimization function and 3D modeling, and I'm using those almost all at the same time. So I have to have something that is really powerful, and this computer is driving me absolutely insane. So I can do most of my work. It's just taking me longer than it usually does, and I've elaborated that to my boss, and he's fine with that.
So most of your work is design and simulation, not actually in the lab.
So we've gotten a new coding manager within the last 6 months, I would say, and he has over 25 years of experience, hands-on doing codings. He fixes the chambers. He knows he he can design a coding without using any software. He's pretty good. Like he can calculate refractive indexes in his head, and he's just a really good guy. So I get to learn a lot. I'm really blessed to have him now, because before I was riding solo, and then it was a lot of troubleshooting. So now that I have him as a sounding board, it's kind of more fluid. But definitely there was a learning curve when you leave college to go to do this. I was spending a lot of time at work just learning new things, learning about coatings, learning about as much as I could.
Who else
I
has
forgot I had this last slide. I just wanted to say, like, half of the optics that are on the Mars 2020 Perseverance rover are coming from our factory in Japan. And some of our other applications and industries that we directly serve would be laser eye surgery, laser tattoo removal, laser hair removal, and like I said, laser machining, laser welding. I forgot I had this slide. I think I just added it maybe this morning.
So who else has a question? I mean, some of you guys are going to be on the job market soon. Somebody must have a question about what he does.
So you mentioned like spending a lot of time kind of learning on the job, but how well do you think that like a physics background prepared you to go into industry?
That's a great question, honestly. So there's certain things, like there's a part of my job that is very much engineering based, which is I've had to learn at the job, but I'm blessed to have a colleague that's has a background in biomedical engineering. So he's familiar with both engineering, but he's very smart with bio stuff and physics stuff as well. And my boss is very patient with me. My boss has paid for me to take a 3D modeling class that I literally got to go during work to this place that's near Cal Poly. And for 2 days, I just trained on how to use the 3D modeling software. So most of the time, like, it's, if there's stuff you don't understand about the job, it shouldn't be an issue, because I think you probably heard, like, physics gives you this like kind of like a tool belt or utility belt of like how to go about solving problems in the world. And so I think, especially at Cal Poly, then you should be fine. Like I don't think any place wouldn't hire you without the, presumption that you would be able to learn whatever you need to on the job. And I'm still been here for almost 2 years, and I'm still learning things about all of our products because we have over 15,000 items in the catalog. There's no way I could know about everything, but so I'm constantly learning. As long as you're constantly learning, constantly trying to improve and better yourself and be better at the job you're doing, then you're going to be great. You're going to be fine. But
Go ahead.
yeah, and I wish there was some sort of connect between like looking at, because what you'll see probably a lot is like these technical drawings, which I had no idea about. But once you get the familiar of it, like the hang of it, it's not too bad.
When you mentioned about them sending you to that software training for the 3D modeling, one thing that has struck me is when I look at how much companies pay for software training, whether it's the 3D modeling software or a ZMAX class offered by ZMAX, if you start translating this into dollars per hour, it's really not that different from college tuition. And I bring this up because you'll hear a lot of criticisms of college costs. Certainly being on the inside, I could say all sorts of things about some of the things that drive up the cost. But then you look at what the private sector is willing to pay per hour for software training, and it's really not that different from college tuition. And it says something about the value that the private sector is willing to pay the same amount per hour that you're paying.
Yeah, exactly. I also wanted to throw out there as well that if you guys ever, I never felt like I could have had enough free time, but maybe you guys do. But they offer these online classes through the UCI Department of Continuing Education. And so my work has also paid for me to take, I'm taking one right now. It's called Introduction to Lens Design. So it's kind of would be like an extension after what you guys learned with ZMAX would be like, this would be the next natural step after that. So even if you're feeling like you weren't as prepared, if you took one of those classes and got to get some more hand on with ZMAX and with an engineer from a big company, then you'll feel real comfortable. After taking these kind of classes too, I feel like, wow, like I was so scared of it, but it's really not that bad.
So you would say that this class is a good natural intro for what you do at the UCI class?
Oh yeah, definitely 100%. 100%. They use ZMAX as well. I took a class that was more geared towards people who haven't used ZMAX before, and then people who are very skilled with 3D modeling. And so I thought it was going to be the opposite. And so that one was a struggle because they were teaching all the basic stuff that we learned in ZMAX with some additional like optimization features that we were learning. But then it was like they expected you to know all the 3D modeling, and that was rough. But yeah, I'm really happy that my work is really willing to pay for me to take classes. I think most people's works would definitely allow them, want them to learn these type of things.
Who else has questions?
I have a few.
Yeah, go for it.
Are you guys using SolidWorks?
We use a program called Autodesk Inventor, but if you can just translate it through a step file anyways, and it doesn't really matter.
Cool. I was wondering if you could talk about a little bit of the manufacturing process of what machine do you use to make a lens?
So it's an interesting process. When I went to Japan, my company, again, I can't say how lucky I am to work for this company. They sent me to Japan for a month to train on how everything is made, from the lenses to those manual motorized positioners, all that kind of stuff. And so basically, they start off with a big chunk of glass, and then basically they cut it into these kind of squares, and then from there they chuck off the square part into a diameter, and then from there they take it and they make it almost near the same radius of curvature that they want it to have. And then from there, it's kind of a complex thing to explain, but basically we have these things called test plates, and the test plate is made at somewhere separate from our facility. And so what it is that the test plate is made with the interferometer, and it's made with such precision that it's like the exact surface, the perfect radius of curvature. And so basically, once we have this and it's documented, we know that it's going to be that exact curvature. So then we essentially make, how do I say it? Like a mirror, or like we take some kind of adhesive, or like, I don't know how to explain it, but basically it's like we coat that tool. And so basically we kind of put this kind of, I won't say it's similar to tar, but it's not like exactly tar. It's something that's kind of used for grinding. And so we put it along that curved surface, and then basically we'll strip that away from the tool so that we don't damage the tool. And so we know that by putting this uniform layer on, that it's going to have the same curvature. And then basically we use this slurry, which is kind of like if you could imagine, it's like a polishing like liquid, and it's got like these little tiny fine particles in there. And so it kind of just does this kind of like I don't know how to say it, like a circular type movement over the lenses.
Is
And
this
so that's basically,
magnetoreological finishing?
what was that?
Is this magnetoreological finishing?
This one is not, but we do have that technology though.
Okay.
The magneto, the what Dr. Small is talking about, it's called MRF, and basically it's a really interesting thing to watch. And so basically there's this little kind of very powerful electromagnet, and then they use the slurry that they use has iron particles infused into it. And so basically it allows, they can basically drag the slurry over the top of this very powerful electromagnet at high speeds. And so only this kind of slurry touches the surface of the glass. And so with that, you can get super high, like really high quality finish that you wouldn't be able to get with kind of other traditional manufacturing. The only disadvantage to that method is that you can only do one piece at a time, where other manufacturing methods you could do hundreds, or maybe almost 1,000.
Got it.
Yeah.
So
yeah, it's a really interesting technology though. It's one of the technologies that allows for aspheres and non-spherical surfaces.
So when you have the big chunk of glass, do you set it in like a lathe? Do you guys use a lathe or a mill? Like what specific machines do you use?
We do. I didn't see a lot of lathe work because the kind of glass that we're doing like isn't, I don't know how to say it. It's not lathe friendly, or it's, I don't know how to say it. I associate like lathes with flame working with hot glass. And that's just not what we do. But essentially, yeah, you're right. The glass can come in two ways. We have this huge BK7 blocks, because BK7 glass is like one of the most common types of glass you'll see. It's everywhere. Everyone uses BK7 or a BK7 equivalent. And so we have huge chunks of this. We'll cut it up in using like a wet saw. So we cut it up into smaller pieces, and then from there we'll get them into like a general size. And so like basically imagine like a 50 by 50 square that's like maybe 10 millimeters thick, and then that's going to make like a 30 millimeter diameter lens. Because basically what's going to happen is, if you imagine the square, it goes onto this machine that basically grinds the edges away. It's called an edge grinder. And so basically after it grinds the edges away, you're just left with a bunch of spherical, like I guess it's a large cylinder of glass. And then basically from there we like separate them, and then you would do the individual machining on each one, and then put them all into the kind of the slurry grinder. And then that would be like one of the last steps you would do. But there's sometimes where it makes more sense, if we're doing like a small batch of something, you can go to the glass manufacturer and say, hey, I want you to send me the glass in these blanks. And so the blanks is basically the size, what I was telling you before, the 50 by 50 by 10. You can specify it to already come like that. So when it already gets to the facility, we just move right into the other grinding. We don't have to do any other, like cutting up a big block into precise, shapes. So it kind of varies. It just depends on the glass type. If you're working with a specific glass and you only need a certain amount, you're never going to buy it again for another 6 months. It just makes sense to get the little blanks. But if it's something you're buying in huge bulk, using all the time, then sometimes it makes sense to buy the big blocks.
Anyone else? We can take one or two more questions. Do you think that OptoSigma is going to be hiring in the near future, or has everything been put on hold with the economic slowdown?
I'd say right now, definitely it's going to be on hold until obviously we can get back into the office. I think we're all trying to stay as busy as possible and, just try and keep. The only reason we're even allowed to be open is because we serve industries like medical and defense and stuff like that. So we have to serve those customers first, and then everyone else we're just trying to keep everyone else happy, because although we do have those important customers, we have so many other customers who don't really fall into that kind of umbrella that are still open and stuff. But yeah, I think we are growing as a company. So definitely if you see something or if I know that we're hiring, I'll send Dr. Small a message and he can let everybody know.
Okay. Any last questions? All right, I don't see anyone's mics turning on. So Kyle, thanks so much for doing this. It was really useful to know what you're doing and that some of the stuff you're talking about overlaps with what we're doing in this class. I hope I'm able to see you in person at an Optical Society meeting in the near future. Yeah,
definitely the one sounded pretty interesting. The next one, or at least the virtual one. Definitely, hopefully in the future. We can only hope,
sounds good.
Hope things will get better.
All right, thanks again.
I'm going to stop sharing so you can have the control.
Okay, thank you. Take care. Bye. Okay. Then let's go to that. All right, so hopefully Kyle has made a sufficiently compelling case to you for why we are working with thin films. So let's continue with thin films. So last time we were talking about thin films. We talked about the phenomena of color in thin films, their use as anti-reflection coatings. We walked through the rules for phase shifts, for looking at the reflection from the first surface and the second surface and the difference between those phases. We looked at how the thickness of the film determines the width of the reflection or anti-reflection peak or trough in the curve. And we talked about why it is that you get a half cycle phase shift when you're reflecting off of a higher index medium. And so now I want to talk about why the color changes with angle. And it is very tempting but wrong to assume that the entirety of this path is an extra distance. And the reason why it's wrong is that if I were to look at, say, the first reflection or the second reflection, yes, all of this is extra distance traveled in the glass. But then when we get out here, you look at this path in air and this path in air, the first reflection also has some extra distance. And this extra distance here partially cancels out the extra distance down there. And so we're going to try to understand that. The other way to think about it is that the light traveling through this coating is undergoing a phase shift. And there's two things that drive the phase shift. There's the y component of the k vector, which depends on how far you translate along the vertical direction. And there's the x component of the k vector, which gets multiplied by the horizontal distance. Now, we know that ky is going to be k naught times n times sine theta, n sine theta times 2 pi over lambda. And 2 pi over lambda naught, 2 pi over the wavelength in vacuum is what I should really be saying. And 2 pi over the wavelength in vacuum is the same here and here. N is different here and here, but sine theta is also different. And we know that n sine theta is the same in both media. That comes from Snell's law. So if I have a wave that could either start off here and go like this, or start off here and go like that, in the end, when it gets out to infinity, it's gone through the same shift delta y if it gets out to the detector. So it's going to have the same delta y, it's going to have the same ky, so that phase shift isn't going to, the phase shift due to the vertical distance traveled isn't going to be any different, right? We're going to have ky delta y the same on both paths. But kx times delta x, well, this delta x, this distance traveled along the x direction, d, and then another d, that is going to be different. And so what you're going to have is 2d times k cosine theta 2, the cosine of the angle in there. So in any problem that we are doing, anytime we want to solve a problem and figure out whether we get constructive or destructive interference, we would, instead of calculating the phase shift as 2d over lambda over n, I would do 2d cosine theta 2 over lambda over n. Any questions on that idea? So let's look at a tangible example. We've got air, oil, glass, and we want to find what wavelengths are strongly reflected, or which wavelengths undergo constructive interference. So let's say we send in the light at a 45-degree angle out here. Okay, so we've got this reflection, we've got this path, and this path, the phase shift due to the distance traveled is going to be 2n2 d cosine theta 2 over lambda. We're going to subtract off the reflection phase shift, 1/2, and we're going to set that equal to m to get constructive interference. And so we're going to get to 2n2d cosine theta 2 over lambda is n plus 1/2. Now the thing is, the mistake that people make so often is they think that theta 2 is 45 degrees. But remember, we have to use Snell's law. The light changed direction inside this coating. So we have to use Snell's law. N1, or 1, times sine of 45 degrees equals N2, or 1.6, times the sine of this unknown angle. We solve for that angle. We get 26.2 degrees. So we get the cosine of theta 2 is 0.897. And then we can start plugging in, and we get that lambda is 2n2d times that cosine factor, 0.897, over m plus 1/2. Any questions? If you wanted to think about it geometrically, then what we would have to do is we could find this distance. It would be twice the hypotenuse of this triangle here. And we could do that. But we'd also have to find this distance, which would be the base of this triangle here. And you can work through all of that, and it's going to get kind of messy. But in the end, you get that the extra path in medium 1 is 2n2 times d times sine squared theta 2 over cosine theta 2. And then the extra path in medium 2 is 2n2d over lambda cosine theta 2, or the extra number of cycles. And so I've got cosine of theta 2 in both denominators, 1 minus sine squared in the numerator. 1 minus sine squared is the same as cosine squared, we divide by cosine, and we're left with 2n2d cosine theta 2, just using the fact that, let's see, this hypotenuse is going to be d over cosine theta 2. We don't yet know what that hypotenuse is, but we're going to find it. And this path is going to be y times sine of theta 1. And we can work out y in terms of the tangent of theta 2. And this kind of geometric approach, even though I said I prefer to do it using phase shifts, using the k vector, this kind of geometric approach is used in a lot of textbooks on X-ray and neutron diffraction, which get used all the time to analyze molecules and materials. Any questions? Then let me switch files. Let's go a little bit more into that off-axis. Okay. One question we could ask is, I just asserted that when we do this off-axis reflection off of a higher index medium, we still get the half-cycle phase shift. But I derived that last class by looking at the equations for a wave that's hitting a surface at normal incidence. And so we just have the 1D wave equation. Well, now we're setting up a wave equation in 2 dimensions. We've got something coming in at an angle theta 1, and then it's refracted at an angle theta 2, and coming out at an angle 3. Let's just look at 2 media for now. We've got the incident wave, E incident times a polarization vector times e to the I n1 k naught. And when we dot k with r, we get k naught cosine theta 1 x and n1 k naught sine theta 1 y, and we subtract off the omega t. The reflected wave is going to be almost the same, except we've got this reflection amplitude, this reflection coefficient, and the x component got reversed. So instead of k naught cosine theta 1, we've got minus k naught cosine theta 1 x. And then the transmitted wave looks also a lot like the incident wave, except there's this transmission coefficient, and we replace n1 with n2 in the exponent and theta 1 with theta 2. And now we have to satisfy a 2D wave equation. So we need that the field must be continuous at the boundary, and that the derivatives of the field with respect to x and y must be continuous, so that we can take the second derivatives, which are derivatives of first derivatives. Now, this continuity condition, partial E, partial Y, that's automatically satisfied, because when we cross the boundary, we change, let me rephrase that. As we vary the value of y, we're not crossing a boundary. Changing the value of y won't flip you from, say, these 2 expressions to this expression. Going from here to here to here to here to here, at no point do I change the expression. At no point do I go from using one formula to another. So I don't have any special condition to impose. Likewise, going from here to here to here to here to here, and then so on. That, again, does not change the expression. It's only when we change the value of x at this point, going from here to here or vice versa, do we change the formula. So that's the only place where we have to actually do some work. So we need continuity at x equals 0. And there's a whole bunch of things that we can factor out when we set x equals 0. For starters, we can factor out e to the I k naught y n sine theta, because n sine theta is the same on both sides. So we're left with 1 plus r12 equals t12, or incident plus reflected equals transmitted. And when we take the derivative with respect to x, it's almost like what we had last time. except that when we take the derivative with respect to x, besides getting a factor of I k naught n, we also get a cosine theta, because in the exponents, x is always multiplied by I n k naught cosine theta. And then if it's the incident wave, it's positive. If it's the reflected wave, it's minus. So we get this equation here. Two linear algebraic equations, two unknowns. We can go through the algebra steps, divide both sides by n cosine theta, and then we can move terms around. When we divide by n cosine theta, n2 cosine theta 2, excuse me, we get T12 equals something messy, but T12 also equals this much simpler expression. So we can equate these two, isolate R12, and in the end, what we get is that R12 is N1 cosine theta 1 minus N2 cosine theta 2 over N1 cosine theta 1 plus N2 cosine theta 2. And if N2 is larger than N1, then theta 2 is less than theta 1. So if N2 is larger, then cosine theta 2 is also larger. So if we're starting off in a low index medium, because N2 is high and N1 is low, then N2 cosine theta 2 is going to be bigger than the first term in the numerator. So indeed, we will get a negative reflection coefficient if N1 is less than N2. And conversely, if N1 is larger than N2, then we will get a positive reflection coefficient. Any questions? What I want you to take away from that is just that the same rule still applies. The rule that we use for normal incidence also applies to off-normal. Now, one thing we could ask is, what about total internal reflection? And that's actually a very interesting story. So to handle total internal reflection, let's start by noting that N2 cosine theta 2, which is going to show up in the exponent, I could rewrite it like this. I could just rewrite cosine theta as square root of 1 minus sine squared theta. And then I could use Snell's law to write sine squared theta 2 in terms of sine squared theta 1. And I get this n1 squared over n2 squared. And I can multiply the n2 through. N2 is the square root of n2 squared. So I can put an n2 squared in here, and I get this. This is just so far a fancy way of rewriting n cosine theta, which shows up in the exponent. But for total internal reflection, n1 sine theta 1 is larger than n2, which would imply that sine theta 1 is greater than 1, which is impossible for real angles. But if I rewrite it like this, well, I get something imaginary here, all right? Because I get a negative thing inside the square root, and the square root of a negative number is imaginary. So this is k2x. This is the x component of the k vector inside the coating. And it winds up being k naught times something imaginary. Well, I'm just going to do what most books do and call that I times kappa. Kappa is all of this with the I factored out. And I plug that into the exponent in medium 2, and I get that my transmitted field is an amplitude, the amplitude of the incident field times the transmission coefficient times the polarization vector multiplied by all of this. This part of the exponent is what we had before. Now I've got I times I, which is -1. So I've got e to the minus kappa x. I've got an exponential decay. So when we talk about total internal reflection, we say that no light makes it into the second medium. That's not quite true. A little bit of light makes it into the second medium, but that light decays very rapidly. It's decaying exponentially. And kappa is going to be inversely proportional to the wavelength of light. So if I've got e to the minus something times distance over wavelength, if the distance is a few wavelengths, then this field has decayed to very, very, very close to zero. Any questions? So one thing that people use total internal reflection for is that this field, like I said, is decaying very rapidly. So if I'm over here, well, I don't see any field. But if I'm right here, if I'm within one wavelength of the surface, then there is some light. And so what people will do is sometimes they only want to image things at the surface. They don't want to deal with any stray light from stuff out here. They don't care about what's here. They just want to look at things right at the surface. That's very common in biology. Maybe you just want to look at the cell membrane. You put a cell on a microscope slide, and the only thing you want to look at is the cell membrane and stuff right in the vicinity of the cell membrane. Well, if that's all that you want to look at, then you'll use that evanescent field that will only see a few hundred nanometers within the cell. Everything else out there, by the time you get to the nucleus of the cell, maybe you're not seeing anything if you've set it up correctly. So that's what they will sometimes use the evanescent field for. Dr. Salick, in his research lab, uses evanescent fields to do very delicate sensing. He wants to sense things at minute concentrations. So he's got a fiber optic cable, and I said that fiber optics, that works off total internal reflection. Well, there has to be a little bit of evanescent field in the vicinity of the fiber surface. And so he can sense things that are in the immediate vicinity of the fiber surface. And so he uses evanescent fields coming out of fiber optic cables to do very sensitive detection of biological molecules. All right, so that's how total internal reflection works. Now, what's the reflection coefficient? Well, intuitively, if you think about it, if we're getting total reflection, we better be getting all of the light reflected. A little bit of it is lingering here, but the stuff that's lingering here isn't propagating, right? So if it's not propagating, then there's nothing to leak out. So the rate at which stuff is coming in has to be equal to the rate at which stuff is coming out, because there's no accumulation here. So that reflection coefficient had better be 1, or at least it better have absolute value 1. And if we go back a few pages, we saw that our reflection coefficient had N2 cosine theta 2 in it. And we worked out that N2 cosine theta 2 is proportional to I times kappa. So we wind up getting N1 cosine theta 1 minus I kappa over K naught. And then we've got N1 cosine theta 1 plus I kappa over K naught. Now this is just the ratio of two complex numbers. And if we look at these two complex numbers, they have the same real parts. And they have almost the same imaginary parts except for a minus sign. So these two complex numbers have the same absolute values, just different phases. So the absolute value of the reflection coefficient is 1. So indeed, we get 100% reflectance. Any questions? Well, here's where it gets really fun. Now I put a third medium here. And now I've got this exponentially decaying field, but suddenly it's also a mathematically valid solution to have an exponentially growing field here. And you can say, wait, how could it possibly be exponentially growing? Well, it's not growing out to infinity. Eventually it reaches this third medium, and at this third medium, it can be transmitted. Now, a transmitted field is neither growing nor decaying. It's just constant amplitude traveling out there. And so you can set it up to have some medium where you've got incident and reflected, then some total internal reflection, then a medium where the field could propagate normally again. And you've got this combination of exponential fields in here. And this is called tunneling of light because it's mathematically equivalent to tunneling of electrons in quantum mechanics, meaning that it's basically the same equations as the equation for a tunneling wave function for electrons in quantum mechanics, except that it's not really quantum mechanics. You may be thinking, well, isn't it quantum mechanics? I mean, it's light, and light is made out of photons. Well, yes, in that sense, in the sense that all things in the material universe, as far as we know, obey quantum mechanics. Of course, it's quantum mechanics. But it's not quantum mechanics in the sense that at no point did we bring in any of the ideas of quantum mechanics. All we started from was really Maxwell's equations and the wave equation for light, things that we know to be true in classical physics, even before quantum mechanics were known. And so all of this could have been explained before anybody had learned about Planck's constant. All of this could have been worked out in the 19th century. And so you can get this, they call it photonic tunneling, and people do experiments with that. Any questions? One reason they do experiments with that is because manipulating light is often easier than manipulating photons, and easier than manipulating electrons. And so people will experiment with light to try to get a very clear understanding of tunneling and then compare with electron experiments. And then sometimes people will bring in the quantum mechanical nature of light, and they'll actually detect photons one at a time. And they're basically, this is one of those places where some people search for little hints of physics beyond standard quantum mechanics. You should look up something called Bohmian mechanics, B-O-H-M-I-A-N, named after David Bohm, if you want to learn more about that. Okay. At this point, what I think I want to do is let's just play around with the saw. Actually, you know, let's not switch back and forth. Let's finish with this. I want to talk about one more scenario, and then we'll play in the software. Okay, I want to talk about a thin glass slab. So in a laser, you've got light bouncing back and forth between two mirrors. And the length of the system has to be an integer multiple of the wavelength over 2, because you got all these ripples and have to fit in between the mirrors. So the wavelength is going to be 2 times the cavity length divided by an integer. And m is usually very, very large. So, you know, I once worked with a laser that was 1 meter long, and it was producing 514 nanometer light. So, you know, the wavelength was basically the size of the cavity divided by 2 million. Right? So m could easily be 2 million. So there could be a whole bunch of closely spaced wavelengths amplified together. Because if I take 2 meters, 2 times L, and instead of dividing by 1 million, I divide by 1,000,001, I mean, the wavelength has just barely changed. So we can have a whole bunch of very, 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 very similar wavelengths bouncing back and forth, being amplified. But sometimes you need a very pure light source. So here's what people do. They take advantage of the fact that for certain wavelengths, a glass slab, air, glass, air, has 100% transmission. But then for any other wavelength, it has at least some reflection. Okay, so if we're not at the wavelength that gives perfect transmission, then we're going to get reflection. Now, it might not be a ton of reflection, but still it's some. And the way to see that, you can get perfect transmission is that we've got our round trip phase shift. It's going to be the component of K perpendicular to the interface, multiplied by 2D, right? And so we're going to have 2n2d cosine theta over lambda. We're going to have a half cycle phase shift here, no phase shift there. And so 2n2d cosine theta over lambda minus a half equals m plus a half. And all of that cancels out, and we can get some perfect reflection. Sorry, perfect transmission. All right, well, what that means is that if we look at the transmission, okay, the transmission is going to be an oscillating function. It's going to oscillate between 1 and something less than 1. You can never get zero transmission. There's always at least a little bit of transmitted light. Okay, and let's say that we are not quite at that peak. We've got one of those wavelengths that we didn't want. It's not quite at the peak. So maybe you get 99% transmission. Well, 99% transmission still sounds like a lot, except that you've got 1% lost on each pass through the glass slab. And if you go through it twice in a round trip, you get 2% loss per round trip. So if we make 50 passes back and forth, the amount of light that actually survives, well, it's 98% of 98% of 98% of 98% and so forth, done 50 times. So if I take 0.98 and raise it to the 50th power, I only get 36% of the light saved. I lose 2/3 of the light in 50 passes. And I would get another 36% of 36% if I did 100 passes. So anything that isn't exactly at that wavelength that gives perfect transmission, after many passes, is going to just be completely reflected out. And so this is a way of purifying light inside of a laser cavity. You may be saying, why not purify it by just having a smaller laser cavity? Because if it's a smaller laser cavity, then the wavelengths, you won't have as many possible wavelengths in there. Any guesses to why we don't want to use a small laser cavity sometimes? Any guesses? Well, a laser cavity is an amplifier, all right? And as the light is traveling back and forth in there, it's getting amplified. Now, the farther it travels, the more it gets amplified, right? As a matter of fact, a laser is actually, it's basically like the feedback from a microphone. It's basically like what sometimes happens when I've got two devices on at the beginning of a Zoom meeting before I turn one of them off. We get some sound coming out of my computer, comes out of the speaker on my laptop, goes into the microphone on my tablet. Then because there's some, because it doesn't have perfect fidelity, transmitting all of the, receiving and propagating all of the frequencies with the exact same fidelity. Some of the frequencies get preferentially transmitted and even amplified depending on how loud the speaker is. And so whichever frequency has the highest amplification will get amplified a little more when it goes from laptop to microphone, from laptop speaker to tablet microphone, which then comes back out through the laptop speaker and into the tablet microphone, which then comes back out. And so you get this feedback loop. A laser is basically a runaway feedback loop at one wavelength, okay? And so the larger the cavity, the more amplification you get. But of course, if you want purity, then you have to get rid of all the other ones. And so that's why people will put these thin glass slabs in there. And so what they could do is these little lines, these vertical lines basically represent spikes of represent cavity modes, okay? And only the cavity modes that happen to match up with one of the transmission peaks of the slab will be retained. Maybe you'll be saying, well, there's still many, many transmission peaks for this slab. There are, but even though there are many, many transmission peaks with that slab, not all of those transmission peaks are at wavelengths that the substance inside the cavity is capable of amplifying. Because besides having this cavity confining light between two mirrors, there's stuff in there that can only amplify light at or near specified wavelengths. So we've got all of the many modes of the cavity, and we've got some range of wavelengths that the material inside the cavity can amplify. And then beyond that range of wavelengths that the material inside the cavity can amplify, we put this slab that will reflect at least a little bit of light unless it's at exactly the right wavelength. And that is how we purify light. That is one way to purify light inside of a laser cavity. Any questions? Going once, going twice. I want to talk about one more thing, and then we will play with the software. I want to talk about something called the distributed Bragg mirror. A distributed Bragg mirror is something that we're going to play with in a couple of weeks on assignments, and it gets used a lot as a special type of selective mirror. It's another way of purifying light. What you've got is a whole bunch of layers, each with thickness lambda over 4n. Lambda over 4n1, lambda over 4n2, lambda over 4n1, lambda over 4n2. And let's just say, to make things simple for now, that n1 is the high index medium and n2 is the low index medium. So let's first look at path 1. Makes a round trip in this layer. Well, all right, we're gonna not worry about the phase shift here. There's inevitably some phase shift at the first layer, but we're worried about comparing all of these different paths. The one that just goes like this, the one that goes like that, the one that goes 3 in and 3 out, the one that goes 4 in and 4 out. We just want to know what happens with all of those. So N1 is the high index medium. All right, there's no phase shift due to reflection here. So it's just a quarter cycle, another quarter cycle, or a half cycle. Now let's look at the second path, the one that goes 2 in and 2 out. Quarter cycle, that's a half cycle so far. N2 is the low index medium, so now there is a half cycle reflection phase shift. So quarter plus a quarter is a half, plus another half, that's a full cycle, plus another quarter, that's 1 1/4, plus another quarter, that's 1 1/2. So this is 1 1/2 cycles versus a half cycle. What kind of interference do we get if one of the paths was a half cycle and the other was 1 1/2 cycles? Is there a difference between a half cycle and 1 1/2 cycles? Is there a physically meaningful difference between those two? Nope, no physically meaningful difference. So this path, 1 in, 1 out, interferes constructively with this path, 2 in, 2 out. Now let's look at this path, 3 in, 3 out. A quarter plus a quarter plus a quarter, that's 3/4. No phase shift here because this is the high index medium. So another quarter, that's a full cycle, 1 1/4, 1 1/2. So a 1 1/2 cycle phase shift versus a 1 1/2 cycle phase shift versus a half cycle phase shift. All of these interfere constructively. And we could just keep on going. We could go 4 in, 4 out. That would be 4/4 plus 4/4 is 2 cycles plus the half cycle phase shift there. So the beauty of this is that all of these paths interfere with each other constructively. And that makes for very, very high efficiency mirrors. Now, some people would say, well, why do you need all those layers to make a mirror? Couldn't you just use metal? We know metals have high reflectance. Well, here's the thing about metal. What happens to metal if you leave it out exposed to light? It eventually gets hot. And the very fact that it gets hot means that it's absorbing some of that energy. You might say, well, metal exposed to light doesn't look like it's absorbing. It looks like it's reflecting. And yeah, a polished metal may be reflecting 99.9% of the light. Okay, but it's absorbing 0.1%. And if you've got a laser with the light bouncing back and forth 1,000 times, that 0.1% adds up over 1,000 trips. And so you wind up getting loss. Whereas this is very low loss material, all right? So you can get very high reflection, and whatever doesn't get reflected will get transmitted rather than absorbed. Now, there's two reasons why you would prefer transmission to absorption. One is that eventually something has to get transmitted. Otherwise, the light would stay inside of the laser and never escape. And if the light never escapes the laser, you can't use it. So lasers are basically a balancing between runaway amplification and controlled escape. Runaway amplification helps purify and intensify the light. Controlled escape helps you use the light. That's one reason why you can tolerate some transmission better than absorption. The other reason is that whatever energy is escaping the cavity, not only do you want it to escape so you can use it, you want it to not be absorbed because you don't want your laser to overheat. So these Bragg mirrors, because these are very low absorption materials, the Bragg mirror will give you high reflection at a wavelength of your choice, very, very low absorption. So whatever light escapes, one, well, it escapes like you wanted, and two, it doesn't heat up. So this is used all the time in semiconductor lasers. And this is one of the first things that a grad student working in semiconductor laser design will learn. At some point, they will have to learn about distributed Bragg mirrors because those are what they confine the light between in most of those experiments. Remember how Kyle was saying a little while ago that they just evaporate layers of material? Well, that's basically what you would do if you were making semiconductor lasers. You would evaporate a whole bunch of layers of alternating materials. Then you'd have whatever material is going to actually amplify the light, then a whole bunch more alternating layers. And that would be a classic semiconductor laser. Okay, I think I'm going to stop there with the theory. What we've done so far today is discuss off-axis reflection and Bragg mirrors. On the homework, we were doing off-axis reflection of TE light, transverse electric fields. I don't think I put this in here, so let me switch to something that I can draw with. So I want to give you a little bit of a preview of what you're going to do on the upcoming homework. I'm going to share this screen. Everything that we've been doing so far has been for what we call TE light. All right, we've got a wave coming in. What I've been drawing here is the K vector. All right, now we know that for any electric field, for any light wave, you've got electric and magnetic fields. I'll do these in different colors. We've been doing the case of an electric field coming out of the page. All right, and then B is in the page.
Hey,
So this
Dr.
is
Paul,
called, is there a question?
what page are you writing on right now? I can't seem to find it. And
I thought I was sharing.
go to view options. I'm looking at the wrong one. Okay, thank you. Sorry about that.
Okay, I think, oh, you know what I did? I need to play with the sharing options. I think that what happened was that, let's look at video settings. No, that's not what I want. I want meeting controls. I want to stop this share. I want to, one participant can share at a time. And then I want to share this screen. Okay, let's try that again. Now we should all see that page. Okay, sorry about that. So, incoming field, outgoing field. When I've been drawing the directions of these waves, I've been drawing the K vectors. But we know that for an electromagnetic wave, there's an E field and a B field. And that E, I'm drawing that E so that it's coming out of the page, and I'm drawing B so that it's in the page. So this is called a TE wave, meaning transverse electric, okay? Transverse means that, well, it's coming out of the page, that if I were to draw a plane that has the incident and reflected fields, that the electric field is perpendicular to both. The electric field is perpendicular to K in and K out. Perpendicular and transverse are two words that mean basically the same thing, right? And for TE waves, the equation that they obey is very simple. Actually, I'll write it as this. I'll write it as del squared E equals n squared over c squared partial squared E by partial t squared, right? These are TE waves. And these are by far the easiest ones to do the math for. But then there are also TM waves, okay? And in a TM wave, we've again got our interface, N1, N2, K in, K out. But now we flip the fields around. Now what we've got is that E is in this plane and B is out of the page. All right. And because of that, this is called a TM wave. Transverse magnetic. All right. And so the equation that's satisfied here is that I just realized I need to check something. Basically, partial squared, yeah. Partial by partial x. If I of 1 over n squared partial b, this would be z, All right, so it's a different equation. Now what we need is we need that BZ is continuous, and 1 over n squared partial BZ by partial x is continuous, all right? Those are our two equations that we need. Those are the two conditions that we need to satisfy. And on the homework, you're going to work out what you get there. You're going to find that the reflection coefficient and transmission coefficient are slightly different. And because the reflection and transmission coefficient are slightly different, this is a way to actually get perfect transmission of one of the polarizations in special cases. And so on the homework, you're going to figure out from those boundary conditions when you get perfect transmission of that polarization of light. And then on Thursday, we'll talk about how to apply that in some special multi-layer coatings. Any questions on the basic idea? Okay, there's a question. Should we require partial BZ with respect to Y continuous also? Sure, you could, except that, like I said previously, when we move along the Y direction, we never cross a boundary. And so because we never cross a boundary when we move along the Y direction, continuity along the Y axis is automatically guaranteed. We don't need to impose that. Right? We never cross a boundary. We never wind up changing the form of our equation. It's only when we move along the x-axis that we cross a boundary, and then we have to start worrying about continuity. Any other questions? Then let's go into the Python code. I'm going to start sharing this screen again. I'm going to try to. Looks like I need to. All right, now I'm going to try sharing this screen. Quit out of that. And go into Python. All right, so we've got our Python code. Why don't you pull that up? I'll give everybody a minute to load the Python code. Give everybody a minute to do that. All right, while people are setting that up, I want to do another share. I want to work out the case that we're actually going to do in Python. So we are going to be doing this case, all right? And what we want to get is we're going to get air, glass, air. So we've got our first reflection, half cycle phase shift. We've got this. Now there's no reflection phase shift there. This thickness is D. So the number of cycles will be 2D over lambda over N. So we're going to, or 2ND over lambda. So 2ND over lambda minus a half has to equal, if we want to get perfect transmission, a half cycle, or 1.5 or 2.5, etc. So we're going to get that 2ND over lambda equals M plus 1, or D should be equal to lambda over N times 1 over 2 times an integer. All right, and if we decide that, let's design for 600 nanometers, because it'll be easy to do the math in our heads there. And let's say that N is about 1.5, then what we're going to have is that D is 600 nanometers over 2 times 1.5 times an integer, which for now we'll just make 1. So this is going to be 200 nanometers. And then we go into our code. And let's see, we're going to, we're designing for normal incidence. So we're going to be in mode 0. In mode 0, we'll make sure that the incoming angle is 0. Left medium index and right medium index should both be 1. Our wavelengths were in microns, so let's make our coating layers 0. We're only going to have one layer. Its thickness will be 0.2, and the material will be SiO2. And let's run that. And then we go and we look at our plots. And we get 0 reflectance, not quite at 600 nanometers, but I'm not too worried about that, because if I look at SiO2 of 0. Looks like 57, I don't get 1.5, I get 1.45. So it looks to me like what I should have done is I should have done 0.6 divided by 2 times SiO2 of 600 nanometers, all right? I said that we wanted a layer thickness of lambda over 2 times the refractive index. So the refractive index is SiO2, which is a function. SiO2 evaluated at 0.6. Looks like that's what we should have. So let's try that again. That's what we're supposed to have for the coating thickness. So let's just change that to 0.2065. And then let's rerun. And yeah, it looks to me like we got perfect reflectance there. Now, we could work at other, oh wait, did I put over M plus 1? I did. If I just realized that I made a mistake there. I had in this derivation 2n2d over lambda equals m plus 1. And then I put m plus 1 in the denominator. I should have put it in the numerator. So let's fix that. We don't have to use a super thin film. I mean, if you think about it, nobody positions a 200 nanometer slab inside of a giant laser cavity. A 200 nanometer thick sheet of glass or whatever would be too brittle. So let's make this, instead of 200 nanometers, let's multiply by 10,000. Because if I multiply 200 nanometers, or 2 times 10 to the minus 7 meters, by 10 to the fourth, I'm going to get 2 millimeters. Now, 2 millimeters is something that we could indeed work with. All right. And what is going on here? Should not be taking that long to run, because it's still just one layer. You know what I think was taking too long is the plotting, the field profile. Okay, well, now we see what happens when we make it 2 millimeters thick instead of 200 nanometers. We get a whole bunch of closely spaced peaks. And since I have not yet figured out the tools for zooming in, I would suggest that we try playing around with the range of wavelengths. So let's go from, say, 590 nanometers to 610 nanometers. All right, well, that looks a little more promising. Let's go from 599 to, to 601. And now you can start to see just how closely spaced these lines are if you have a 2 millimeter thick substance. Any questions so far? Now here's what a lot of people do. What they actually do is they'll say 2 millimeters. When you have 2 millimeters, you see how close these lines are, what a mess that looks like. So here's what they do instead. They put 100 micron coating on top of something that's 2 millimeters, right? Because 2 millimeters would be something that is thick enough that you can handle it. You know, it won't be super brittle. So they'll have something that's a few millimeters thick, and then they'll have something that's 100 microns. So let's think about how we would model that. Well, first of all, if we were to just make it, let's make 2,000 microns. So we got 2,000 microns of glass. Now, if I put more glass on top of that, well, there's no reflection at that interface, right? A glass-glass interface, if they were the exact same kind of glass, there'd be no reflection. So what they would do is they would put a glass with a slightly different refractive index there. So let's do that. Let's make 100 microns of something, but instead of pure SiO2, let's maybe do BK7, which has about 1.53. Let's just see what happens. And if we do that, when we switch between the two, we see that the true zeros, you may be thinking, wow, the peaks are still the same distance apart. Yeah, the peaks are still close, but here's something to notice. When we look down here, you see how not all of these reflectances are truly zero? All right? Because not all of these reflectances are truly zero, some of these are not actually what we want, okay? The only reflectances that are actually what we want are the true minima. And because I have not yet figured out the zoom in tools of this one, what I think we're going to have to do is we're going to have to go down and play with that. No, I don't think we're going to. I think that editing code on the fly is a really bad idea. We're just going to note that we can see some physical differences down here. We can see that the reflectance is not truly zero everywhere. But what I want you to take away is that there are a few peaks down, there are a few dips down here that do go truly to zero, and then there are others that don't quite go to zero. And so by putting a thinner coating on top of something that's thick enough to handle, only some of these truly give you the zero reflection that you want. And it's the zero reflection that's going to, it's the zero reflection that will be kept in the cavity. So what questions do people have? Well, for the next assignment, I've finally started to catch up on grading. You may have seen that I graded one of the ZMAX assignments last night. We'll be catching up on that in the next week. For the next assignment, you're going to play with this software and you're going to model some thin films. And some of the thin film specs that you're going to work with are actually from a patent. Because remember what Kyle talked about, one of his senior project was to go read through the patent literature and So I'm going to have you read a patent, and the patent you're going to look at is for anti-reflection coatings on polycarbonate, partly because polycarbonate is useful. It shows up in glasses. Partly because this is one of the more easily readable patents that I found. You're just going to have to, you don't have to read every word of the patent. Just go to the tables that are referenced in the assignment. An important thing to keep in mind is that when they talk about optical thickness, they say 0.25 lambda. They don't mean 0.25 times the wavelength in vacuum. Or when they say lambda, they don't mean the wavelength in vacuum. They mean the wavelength in that material. So if we're talking about, I don't know, reflection at 500 nanometers, that's 500 nanometers in vacuum. But in the material, the wavelength would not be 500. It would be 500 divided by 1.47. And another thing you may be thinking is, well, if it's SiO2, should I use the SiO2 function in the Python code, or should I use the refractive index that they give here for SiO2? You should use the refractive index here. And you may be thinking, well, what is it in reality? And the truth is that in reality, the refractive index of SiO2 all depends on how it was deposited. Remember how earlier today Kyle said that when they deposit a layer, they don't necessarily get the bulk density. They might get a different density than a thin film could have a different density than a really thick material. This refractive index here is the refractive index of the material when it's deposited under the conditions that they're using in their apparatus, okay? So don't type in the word SiO2, type in that number, because the SiO2 refractive index that I'm giving you, that's taken from someone's article where they deposited SiO2 under a particular set of circumstances. Circumstances that are different from the circumstances under which they made the films in this patent. So whenever you see a number in whenever you see a material in the patent, use the number that they give you for that material in this patent. Any questions? I don't have anything else to say. I'll stick around for a few minutes if people want to work in the Python code. And whenever you feel like you're comfortable with it, go ahead and log off, and I'll see you on Thursday. Have a good day.
Yeah, that's kind of cool about the deposition stuff. When we were doing our ice films in Arizona, we found that the size of the dangling bonds we were looking at was very dependent on the deposition angle.
Yeah, thin film deposition is as much an art as it is a science. Some people wouldn't even dignify it with the term art. Some people claim that it's all black magic, that it's all very strange things that no one can truly understand. One of the biggest frauds in physics in the late 20th, early 21st century was a guy named Henrik Schoen at Bell Labs, who was fabricating data left and right. And the one reason why people gave him so much benefit of the doubt was that he said that he was using that, well, a lot of the work came from depositing thin films in his vacuum chamber. And every vacuum chamber gives you slightly different properties for the thin films. And so everybody figured, you know, there's something weird in his vacuum chamber. That's the reason why no one else can get this experiment to work. But yeah, thin film deposition is black magic.
Yeah, we just ended up rotating the thing through about 10 different angles before we found whichever one just gave the biggest bonds.
Doesn't surprise me at all.
All right, I'm gonna take off. Have a good day.
You too. Bye.